All right. Good morning, everyone. Here is the final presentation for our Capstone project. We are working on automatic optimization of practical QA systems, where Aditi Knoshia, Ishani Agrava, Priya Bagria, and Shreya V, and Wayne Wang. We're advised by Professor Eric Naberg. So in the real world scenario, when a user input a query into the web browser or search engine, it's often too short or too brief, and sometimes lack of the necessary context, which is a common challenge faced by existing IR systems. Which would, with this problem, it will result in unsatisfying result for the users. To tackle this problem, we're introducing Qtune, a R-cubed centered plugin, which is retrieval, re-ranker, and rewriters. With our plugin, it would enhance user queries with large language model and RAG, which is retrieval augmented generation, to help add the necessary context to the original query, which inevitable add more quality to the original query. So as for our expected outcome, we would like to see the improvement of retrieval qualities from existing IR system along with our Qtune. For our evaluation, we're majorly focusing on two metrics. One is mean reciprocal rank at 10, and another one is recall at 10. So here is an overview of our system design. When an end user sends us a query, it will enter the RAG query rewriting pipeline, which consists of two major components. The first one is the initial BM25 retriever and the mono T5 ranker. It will get the top N passages based on the given query. Once we get the once we get the passage, we will pass in the original query along with the relevant passage into our LLM rewriter. As for the rewriting pipeline, we have proposed two methods. The first method, we use a pre-trained Llama 2.7b model along with prompt engineering to do the rewriting. And for the second approach, we're using Llama 2.7b, but it's fine-tuned with our self-generated RLHF dataset. Once we get the rewriting query, we pass it into our final dense retriever and the ranker to get the final result, which are the top K ranked passages for our evaluation. As we're implementing this project, we have five major scientific hypotheses. First, we hypothesize that retrieval augmented generation are good for query writing, which can provide better queries. Second, we assume that large language model with prior knowledge is suitable for enhancing queries. Third, we're training our large language model rewriter with parameter efficiency fine-tuning, which would essentially reducing the computational complexity. And fourth, we believe that RAG can improve the search result, especially for tailed and failed queries. Last but not least, we realize that query formation is crucial in information retrieval, as search engines sometimes often migrate to natural language queries. And for our intended user, we majorly focus on two groups. The first group are researchers working in the industry of information retrieval, who would use Qtune to improve their training and benchmarking in multiple IR tasks. The second group are IR business and users who can use Qtune to improve their IR system's general performance, as well as using in organization via internal search. Here are our functionality requirements. First, we would require a valid user query as the input. And we have two different pipelines for information retrieval algorithms. The first one is sparse passage retrieval and ranker, which are used in our RAG pipeline for the query rewriting. And the second one is the dense retrieval, which are used to retrieve our final result. As we're using large language model as a major component in our pipeline, prompt engineering is inevitable. We have using prompt engineering in the following two sections. The first one is that we're prompting GPT-4 Turbo as a human agent to generate the RLHF dataset for the fine-tuning purpose. Secondly, we use prompting engineering techniques to prompt our fine-tuned and pre-trained model to do the rewriting tasks. To focusing on our rewriting focus, we have used the tail queries filtering to filter out the queries that do not need further rewriting. And then next, we have two pipelines. One is to using RLHF to train the model, and another one is to do the query writing tasks with large language model. And finally, we have the evaluation. As we mentioned before, it's MRR at 10 and recall at 10. We will follow it up in details in future slides. Aside of the functionality requirements, we have 6 functional requirements, which are scalability, performance, architecture, usability, regulatory, and interpretable abilities. So we aim to design a system that is adjustable or flexible to be adapted to different system architectures while we're addressing ethical issues, enhancing usabilities, as well as lowering the introduced latency and complexity into the original systems.
So here are the resources that we used for our system. For our data set, we use the MS Marco passage ranking data set. For the model inferencing and fine tuning, we requested access to Llama's model weights from Meta. For our sparse and dense retriever systems, we required the pre-built indexes to be downloaded locally, and these indexes needed to be compatible with both the model and the data set. For the RLHF preference data creation, we needed OpenAI credits. And finally, to run all of our experiments, we used various platforms such as the LTI cluster, Google Colab, and AWS SageMaker. So for our experiments, we exclusively use the MS Marco dev split. The reason being that the trained data set from MS Marco was used to pre-train our final dense retriever, which is Colbert. This is also the state of the art that we will later be using for our baseline experiments. And also we do not use the test set from MS Marco because we don't have the relevance rankings for that available to us or in public. So for our first set of experiments, we use the dev small subset, which is provided by MS Marco. And we do this to confirm our first 2 hypotheses, which is that RAG works for query rewriting and that LLMs themselves have enough knowledge to do query rewriting. For our second set of experiments, we perform it on a much larger query set. So for this, we do this to confirm our hypothesis 1, that RAG works and that our pipeline is working. So for this, we use the entire dev set and we make sure that all the queries are unique in this case. For the third and the final set of experiments, we actually create our own subset of the MS Marco dev set. So we call this the tail query subset. The idea was that we try to identify queries that would require rewriting. And since we don't have any such data set available for MS Marco publicly, we create this by filtering out queries that require rewriting explicitly. So for this, our criteria was that any query which yields a 0 precision at 10 score using our final dense retriever would be included in the tail query subset. And so all of these data sets were used in the experiments that were run to prove both our proposed technologies, proposed methodologies of prompt engineering and RLHF fine tuning.
So as we mentioned briefly before, the initial retrieval was done using BM25, and we used the Lucene Searcher pre-built index, which is a sparse index that's available in PySerenity. And we did a comparative study between MonoT5 and BERT regarding the re-ranking, and we found that MonoT5 seemed to perform better for MS Marco. So we selected MonoT5 as our re-ranker. The output contract depended on how many context passages we were planning to use in our downstream system. So for our evaluation, for example, we used 1 context passage, sometimes we used 2, and sometimes we used 5. So depending on how many context passages we were using, the output contract was changing, but for the most part, it had the query ID, the query, as well as all the context passages and their corresponding IDs. Another very important package that we used was PyGaggle. And then we used LLM models for rewriting. So we confirmed earlier in the semester, we confirmed our hypotheses that RAG would help LLMs rewrite the queries using black box LLM GPT 3.5. And then for our final pipeline, we made use of white box LLM Llama 2, which was the 7 billion parameter model. And we experimented with zero-shot learning, few-shot learning with and without RAG, prompt engineering with RAG, as well as RLHF fine-tuning. So what you see here is a screenshot from the Hugging Face UI that allows you to chat with Llama 7 billion model. And so the prompts that I'm going to show, this one and in the next slide, are the best prompts that we had. But I'm trying to show here a success case versus a failure case. So in this particular case, our prompt was that as a ranking model, your first task is to rewrite queries. And I would like to bring attention to how we've formatted this prompt. It has to be instructional because we found that instructing the model seemed to perform better than conversing with it. We also explained to it that we will be giving it the query and the relevant context and that it had to return a rewritten query to us. We also explained what a good question would look like. And for that particular reason, we say that the intent of the original question must remain while the question is still generalizable enough. And this was because if we did not give this particular instruction, the rewritten query often would carry too much context from the passage that we had given it, becoming too precise and sometimes changing the intent of the original query. So in this particular case, the question that we gave it was what causes women to be hot? And the context passage was information related to menopause and hot flashes, etc. So then the successful rewritten query is what are the potential underlying causes for experiencing hot flashes and excessive sweating beyond menopause? The second prompt also is a success prompt in the sense that it performed pretty well on most of our queries, but this particular use case is where we saw it failing. So this prompt also instructs the model that it will get an original query and a context passage and that it has to return a rewritten query. In this particular case, we also mentioned that it has to be a single sentence because often we were getting multiple sentences back as a result. However, the input query was who plays Tom in Days of Future Past, and the passage talks about Halle Berry, which is the actress who played the part. But the passage also talks about how her scenes were cut down a little bit during the filming. As a result of which, the rewritten query is who currently appears as Tom in recent X-Men films, considering Halle Berry's reduced role in the upcoming movie. So the intent here is changed. It assumes that somebody else plays the part because Halle Berry's part has been cut. Other than this, we also experimented with and without RAG, as I mentioned before. So without RAG would be basically asking the model to add context based on the information that it already had in its training process. And so we would say things like, add more context to the best of your capability and give me a rewritten query. Attention to be drawn to without asking for further explanations, because oftentimes when we are asking the model to add context on its own, it would ask us to give the additional context, which was kind of losing the basis of what we were trying to do. And then with RAG, when we're adding context, we found that queries like rewriting a single question to improve retrieval results using context given above was a good one. So during this entire prompt engineering process, we realized that the model is extremely sensitive to what you give it, and that the prompts have to have a very fixed structure in order to get the results that we want. But at the end of the day, there is no one single template that can guarantee a very good result.
So here's the design for our prompt engineering experiments. As you can see, once we have the original queries, we use as context and drag either the gold standard passages from MS Marco, or for a more fair and real life like comparison, we use the top K passages that get retrieved using our sparse retriever system, which is BM25 and Mono T5. And here K varies between 1, 2, and 5, as mentioned earlier. So once we have all of this information, we also have a bunch of prompt templates, which we generated using the prompts shown earlier. And then we basically populate these prompts and we batch them and send them to our Llama 2 7 billion model for the generation of the rewritten queries. So for this case, we particularly found that VLLM library was extremely helpful for fast text generation inferencing. So we were able to significantly speed up our experiments because of this. And once we had the rewritten queries, we would send it to our dense retriever system, which was using the state of the art Colbert to encode the queries. And for the passages, we used the pre built index that was compatible with this. For the dense vector search, we used FICE. And finally, when we had our final top K retrieve passages, we run that through our evaluation module and get the relevant metrics to evaluate our system.
So as the second technique for automatic prompt rewriting, we fine-tuned our rewriter plugin of RAG with LLM and used an approach analogous to RLHF fine-tuning of LLMs. So we use an approach called direct policy optimization through pseudo-human feedback. DPO is basically an extension over RLHF. It simplifies the process of explicitly training a reward model by treating a constrained reward maximization problem as a classification task on human preference data. The entire process can consist of three main stages. First is the pseudo-human feedback data generation. Second is the supervised fine-tuning. And third is the RL fine-tuning using DPO optimization. All of this fine-tuning has been done using parameter-efficient fine-tuning techniques. Here we use LoRa and 4-bit quantization to be able to fine-tune in a constrained resources. So let's just double-click on each stage for further clarity. Firstly, we need to create this preference data for any RL-based fine-tuning, and it comprises of a triplet of an original, chosen, and rejected queries. In order to create this data, the generic approach is to have humans manually create it, but we wanted to automate this process, hence we used GPT-4 as a proxy to human. We prompted GPT-4 to rewrite multiple different queries and rank them based on the relevance of the given relevance to the given context. So here you can see the prompt and where we ask GPT to rewrite a good and a bad query. In the prompt, we provided the context to the GPT as to what is defined as a good and a bad question. And this really helped it to understand create a major difference between the good and the bad query when using GPT-4. Next, to start the RL fine-tuning, first we do SFT, which is supervised fine-tuning. So given the original query and the good rewritten query, which was created in the previous stage, a pre-trained llama is fine-tuned with cross-entropy objective. This is done to approximate a desirable behavior of rewriting in our llama model. Why we did it is because in our initial analysis, it was observed that off-the-shelf llama is not very good in the task of rewriting. It tries to answer the question instead of rewriting it. So in order to make it understand that task, we did the supervised fine-tuning. Once this was done, then the previously SFT fine-tuned llama is used in this RL-based fine-tuning using DPO, and it is used as both the active and the reference model. So this is to ensure that the RL policy doesn't stray away from the original model. The DPO loss is calculated by taking the difference between the chosen and the rejected log probabilities from these SFT LLM outputs. Finally, so the entire model is trained to increase the likelihood of outputs that align with the preference data and decrease the likelihood of the non-preferred outputs. So let's now look at the results. So these are our preliminary results, which was conducted in the first half of the semester with the black box LLM ChatGPT 3.5 to validate our hypothesis. So because of absence of any rewritten queries in the data set, we are evaluating based on the output of the downstream retriever, which we call as a frozen retriever here. Hence, our metrics are MRR at the rate 10 and recall at the rate 10 for our results. Key observations made here are, firstly, a pipeline of LLM-based rewriting is better for the IR or QA systems, which has dense retriever as a downstream retriever rather than the sparse ones. Secondly, we have two baselines marked in gray. So one is without using any rewriting module, and another is like without RAG. We just use LLM for rewriting. And here we can see via experiments 8, 9, and 10 that RAG pipeline works better than just using an LLM to rewrite. Also, using an oracle retriever with LLM crosses the main baseline of not using any rewriting module as well. Finally, we also see that using our own retriever, performance increases as the number of passages, we were increasing the number of processes from 2 to 5. So this gave us the promising scope of improvement, and hence we reran these experiments for the white box LLM as well, which was Llama, which was the final LLM we wanted to use for our Capstone project. So here also the previous hypothesis still holds, but Llama, one thing observed was that Llama performed poorer than GPT. Error analysis again showed that, as discussed before, that it's mainly because Llama suffers from not being explicitly able to understand this task of rewriting. Even like normal prompting LLM, we had to do few shot to be able to get some good results out of it. So in the second half of the semester, we majorly focused in fine-tuning Llama, either by RLHF or by prompt engineering. And we see that using both of these techniques, the results improved. However, prompt engineering performed better than RLHF fine-tuning. And we can discuss more why this happened in the later stages. One more observation was that apart from experiment 5, we still couldn't find across the very first baseline we had. And based on the deeper analysis, we observed that maybe because their small data already had complete queries, hence the baseline is very high enough to beat, and queries doesn't require much of the rewriting. And this actually led to the creation of the tail queries, as mentioned previously.
So next, to reconfirm our hypothesis, one that our RAG pipeline is working well, we actually ran the experiments on a much larger data set because our previous ones were on the dev small data set. And in this case, we used as baseline the state-of-the-art Colbert model, which is also our final frozen retriever. So, and then for our comparison, we ran our best prompt, which was the best model so far in the white box LLMs category. And we, as context, used the gold standard passages. And here we saw that there was a 2x improvement in the MRR score. So for our final set of experiments, as mentioned earlier, we run it through the tail query subset, and this is to only run the experiment on the queries that actually need rewriting so that we can evaluate our system on that. So again, here as baseline, we use the state-of-the-art Colbert, which is our dense retriever. And for our prompt engineering experiments, we actually ran the experiments on the top 3 prompts that we got from our dev small experiments. But here we're only showing the results for the best prompt that we have received. We can see that across the board, all our proposed methodologies were able to beat the baseline of Colbert. And we also see that uh, using gold standard passages as expected gave a significant improvement over the baseline. But since in real life we will not have the gold standard passages available to us, we actually use our initial sparse retriever system to retrieve the top K passages, and we run multiple experiments for that. So in that case, we saw that for the RLHF tuned model, there was a 3.5x improvement in the recall at 10 metric over the baseline. And for our best prompt engineered model, so the best prompt with the pre-trained llama model, we actually saw that for top 1 passage retrieval, we got almost a 5x improvement in recall at 10 over our baseline. So this kind of confirmed our hypotheses that RAG especially helps with tail queries because we saw such huge jumps in our metrics.
So we had conducted some error analysis on the RLHF preference data, which was created through GPT. The first and the foremost thing we saw was that in a lot of rejected queries, we could see that that GPT was taking answers from the context passages and infusing them into the questions directly. For example, if the original query was average GPA to get into UCSD, the rejected query is 29 the GPA needed for UCSD. The second thing we noticed was that irrelevant questions were being used as rejected queries, which stems from the fact that it picks up some information from the context passages as well. For example, what is a Nosta? Nosta over here, I believe, means nostalgic, but whereas the rejected query talks about what does homesick mean. The third pattern, which was a very surprising pattern, which we noticed, was that in a lot of instances, the rejected queries were more semantically closer to the original query than the accepted query as well. And although we want the accepted query and the rejected query to be like similar in terms of what the question is, but we do not want them to be exactly identical to each other because RLHF requires really high quality data to train on. And we believe like very identical questions would probably confuse the model as well. And we had also conducted qualitative analysis on the best performing prompt engineering model, and we saw two major like pros to it. The first thing we noticed was that we could see that the rewritten query has a better sentence structure and definition compared to the original query. For example, what are asteroids question mark kids getting rephrased as what are asteroids and why are they interesting for kids to learn about, which makes more sense and like is more human interpretable. And second thing, which we believe really helps the retrieval process, is that it adds context and definition whenever there is some kind of ambiguity in the query. For like example, how many regions are in GA? Although we know what GA stands for in this case, which is Georgia, but the rewritten query like rephrases GA to Georgia, which we believe helps the retrieval process as well. And we also noticed few cons. First pattern we noticed was that the rewritten query sometimes intends like a wrong meaning, even though the right context was given. Something like what is Donald Trump's wife name, and which gets rewritten to what was Melania Trump's name before she married Donald Trump, which was not the intention of the original query as such. And the other pattern was that in few cases we could see that wrong context was provided to the query, and in that case it completely throws off the rewritten query, and it talks about something which is not relevant to the main query as such. These were our milestone plans, which helped us judiciously plan our resources towards the whole of the semester. Moving on to the future direction, the first and the foremost thing we would want to do in the future would be to have human annotators create the RLHF preference data. Because of resource constraints and time constraints, we had to resort to using GPT for this. But moving on, we believe having human annotators to collect this data would make much more sense. The other direction we would want to work on is evaluation with the final answer rather than with the documents retrieved, which we believe makes more intuitive sense as well. And doing retrieval augmented generation from information from Wikipedia and other internet resources would also be a potential way of working. And reflections. Throughout the project, we actually came across a bunch of surprising and interesting things we learned. And to summarize them, what we noticed was that prompts are extremely sensitive and requires like formatting. And even if there is a small change in the prompts, it really affects the rewriting task, which also means that zero-shot prompting actually yields better results compared to few shot prompting. And the choice of few shot example also really affects the rewriting task. And as we are using models like Llama 7B for fine tuning, we also need to resort to techniques like parameter efficient fine tuning and quantization because of resource constraints. And yeah, thank you presentation. And we thank our mentor, Professor Nyberg and Annette, and all other professors who have been with us throughout the project and helped us through our ups and downs. Thank you.
So thanks for the presentation. I think you guys covered a lot and you learned a lot. But I wasn't quite sure what RLHF was. Can you go to the slide where you defined that?
Yeah.
Okay, RLHF. So it stands for reinforcement learning from human feedback.
Yes.
Right? So I think this is a really interesting idea because in a practical world, you would definitely be putting a capability like what you're doing in production. You would want to be getting feedback from users, both in a sort of pre-release testing phase and also once it's out in the wild. And I think that the idea of using ChatGPT as a proxy for the human was an interesting way to get started on this. But there was a lot of detail there, and you went through it kind of quickly. Can you summarize for us what you think you showed with this and what the next steps are? Because that wasn't quite clear to me. I got the idea that you were able to actually do the reinforcement learning and that you felt that it helped. But later on when we went through the results, it wasn't clear to me whether this is something that we would always want to have and sort of how we would continue to improve it. Could you summarize that?
Yeah. So RLHF fine tuning, like our main hypothesis was like by creating this human preference data in order to tune this entire llama, it will help us to align with what we want as a good and the bad rewritten query. So with that objective, we did this RLHF fine tuning.
Okay, so there's an assumption
yes.
that you're always going to have multiple strategies for rewriting, and you want to somehow rank those or classify those so that you can pick the most likely one to go forward with?
So during our preliminary analysis, we saw that if we don't do fine tuning of llama or LLMs, there was various variation on how it rewrites the query. We ourselves had this assumption. We ourselves and saw that this is a good way of rewriting, whereas this is not a good way of rewriting.
So the way I should think about this is that if I suddenly give you a new language model that has a gazillion parameters and I really want to use it, you have to go through a procedure like this to figure out which kinds of rewriting will really work there.
Yeah.
Okay, so I think what we've gotten to here is maybe a layman's understanding of what the role is here, and I think that could have been explained a little bit better. But I think we all understand, what the phenomenon is, right? So maybe in the final report, make it clear that you're motivating this by the idea that we always have to be ready to use a language model. We always have to be able to adapt to it because it's very sensitive, and it would be expensive, to sort of use a human to evaluate all the rewriting. And anyway, we need to know what the language model thinks, right? Okay, very good. So can you go back to your hypothesis slide? So I didn't understand what the difference was between H1 and H4, because I think RAG is going to provide better queries overall. And then there was a specific hypothesis about RAG for tail queries.
So the reason for this was that initially in the first half of the semester, when we were running some experiments, we saw that there were a lot of queries that did not actually require rewriting at all because they were perfect by themselves. So, and a precursor to our pipeline ideally would be a classifier that finds out whether a given query requires rewriting or not.
Okay.
But since that was a completely different tangent to our project, and that required considerable efforts, we thought that we would approach it in two ways. One, we would evaluate on the entire data set. And second, for H4, we would just iterate over the failed or tail queries and see whether we have a significant improvement for tail queries compared to the entire set.
Good, and I'm glad that you did that because the numbers, on the results slide were really high across all of the conditions. And when you're putting a technique into practical use, usually anything that's that good, you don't care whether it's 93 or 92. You're actually going to pick the thing that's cheapest and easiest to use. So I really like the idea of focusing on what you're calling the tail queries, and that could have been, more of the focus. I think of what's here because if you look at the frustration that users feel, they say something the way they want to say it, and then they get back, crappy results that they don't want to see. So that's a good focus. I'm glad that you had that, in the work. It's just that when you presented the hypotheses, you hadn't kind of explained what tail queries are yet. So probably my advice would be that if you're going to present this again, like as part of a job talk or something, you want to really spend more time talking about the domain. You kind of jumped in, assuming that you'd be talking kind of to an IR or QA audience, and it probably would have been better to do some kind of sort of notional use cases where you show what happens to a user, when certain things happen. That would have given you a chance to explain what all the acronyms are, and then motivate sort of the kind of boxes that you're putting in here. Now, granted, when we started this project, I was having you focus just on the three-phase architecture, and I didn't emphasize this maybe as much as I should have. But thinking ahead to how you want to explain this research to other people, you definitely want to think more about what the user use cases are, and then what the real failures are, of the current technology and how what you're doing help there. Can you go to your NFR slide, non-functional requirements? So do you think you evaluated any of these in a concrete way?
So there wasn't any evaluation, but we would say that we kept our architecture in mind. Like we keep non-functional requirements in mind while creating our architecture, and that's why we have this plug and play of rewriting module and have a frozen retriever ranker in afterwards, so that our rewriting module can be plugged in for any IRQA system, irrespective of what the team is using.
So you would say that your design was informed
Yes.
by these non-functional requirements, and I guess we'd have to have somebody try to extend it. Okay, I think that's reasonable. Can you go to slide 9? So it wasn't clear to me whether you were doing cross-fold validation and whether you were, testing on training data here. So I think it would be, you should answer me now, but also the final report needs to be quite clear on this. Because if you pick the dev small subset with 1,000 queries and then you train on that and then test on it, there's probably a loss of generality there. So can you comment?
Sure. We actually mentioned this during the presentation that we do not use the test split at all, and that's because the final dense retriever that we use was pre-trained on this. So we didn't want to introduce any bias from the train set in MS Marco into our pipeline.
Okay.
And also the test set was something that we could not use because MS Marco does not release the relevance rankings for that. So for our development process, we felt that wasn't very helpful. And we were completely focusing on the dev data set. And the reason we use the dev small over there was not for fine tuning. So we use that essentially for our prompt engineering experiments and to select our models. So for instance, we selected the white box LLM Llama. We also figured out what would be our initial retriever and ranker through that because we did some intrinsic evaluation and found that BM25 plus Mono T5 was better than using BERT over there for our case. And for the last experiment, that's the only time when we split our subset into the train, test, and dev split. And specifically here, we use train to actually train our RLHF model, and also to, because this is what we were using for the RLHF model, we also use this to figure out what is the prompt that is giving us the best result for the tail queries. The test split is used for all of our evaluations later on to keep it completely segregated from the train split, and also to test our experiments on the same test data set across all of the models. The dev split here, which something we should mention earlier, was that it was used only by the RLHF model for the hyperparameter tuning.
Thank you. So I think the big learning here was that even though someone might think that you can develop a pipeline that includes prompt engineering and fine tuning and so on independently, we found that they're very interdependent and they can't be developed independently. So if you're going to do this project over again, let's say we rewind back to January, but now you have all the insights that you already have. Would you have done things differently? Would you have emphasized a different development order or different research questions? How would you be influenced by what we learned?
So for
So when we started out, Professor, we didn't have LLM models, like mainstream LLM models. It was just starting out. So we did not think of that direction. We were like majorly looking into using other primitive techniques to expand. So I believe like right now, if we would start, we would start out with prompt engineering and RLHF with that as the main focus, and would have like tried knowledge distillation as well. We did not have enough time to like fully explore that part because we came to that only this semester, and we could not like fully delve into that, given that we had to start building the model as such. I think we could have focused on that even more.
To add on to it, like for prompt engineering, we would do a more structured way of handling it, like using maybe some chain of thought, like other way of handling this technique rather than trying prompts our way. Like that's a kind of a manually exhaustive technique of trying prompts one after the other. Right. So have a more structured way of handling this prompt engineering tuning.
Yeah, so adding on to what Ishani said, With respect to prompt engineering, we didn't actually realize it was going to be that big of a task because we didn't know how sensitive models can be to the prompts you're giving them. We realized things like capitalization or even going from terms like context to context passages would completely change the output that we were getting. So in order to have an exhaustive way of figuring out like different types of templates that we can think of, would have been a bet like something that we would probably work on more rather than manually feeding because you can only try so many prompts manually.
Right. So based on what you learned, now you need to create an automatic system
Yes.
to basically do tuning of a basic prompting approach to find out exactly what format it's going to work best.
Exactly, because there's no specific template, no one template that gives us the best results. So we need to try out a bunch of things before we can exhaustively like decide what we want.
Thank you. Any other questions from the group?
I guess it surprised me that that you talked about using RLHF in your process, but didn't like you almost mentioned it in passing and didn't mention any technical difficulties with getting it actually to work on our infrastructure here. And what I have heard people say is they really had to clamp back on how they applied it in order to even be able to do it with the resources we have. And so I guess I just wonder, how did you pull it off? And so what compromises did you have to make, and how do you think that affected the result that you got out?
Yeah, so for RLHF, first thing, like without quantization, like we had to load the model in 4-bit quantization, and without using LoRa or PEP techniques, it wasn't possible to even start the fine tuning on it. So these two techniques were essentially important. And how did these affected was that we couldn't use the prompts we had with prompt engineering directly for RLHF. We had to do like another few we have to modify the prompt specifically for RLHM and make it as small as possible in order to fit it into the context length, because if we keep increasing the context length as well, that was increasing the time again. So there was another set of these challenges of tuning the prompt, tuning the parameters, and being able to work with the quantized model, because the quantized model was giving different results than the actual model results which we observed during prompt engineering. So these two, so we couldn't directly utilize our efforts made during prompt engineering into RLHF, and a separate set of efforts have to be applied during there. And one thing, so we didn't focus more on this because we were hoping we would get good results with RLHF, but it didn't. And majorly the reason would be because of the preference data which we created, and they showed that it had a very specific pattern it learned, which wasn't getting translated into our, which was negatively impacted the learning of our model. So those were the challenges, I would say. And from the training perspective as well, like we had to reduce the train set, like optimize the train set as much as possible, like keeping it big enough but small as enough as well, so that we can do this entire training in like 3 to 4 hours. So yeah, that was it.
So it sounds like you had the same challenges.
Yeah.
And ended up not being sort of like on the critical path to.
Yeah, so I guess it's a follow-up question then, and I guess this is kind of related to the one that Eric was asking you. So my impression of your process is that you had constraints on the data side and on the time side, and there was a whole space of things that you wanted to be able to try, and you kind of expected some things to kind of pan out a little bit better than they did. It seems unfortunate that the thing that got pushed to the wayside in favor of spending time on RLHF, which didn't really pan out so well, was the distillation, which I think that there's been a lot more work in the past on, and might have played out better with the resources that you had. So I guess I wonder now, looking back on the opportunity and the time, whether you would recommend to, say, the next team that comes in and follows up, whether there are any ways that you would have, reprioritize the way that you use the resources that you had.
I think if I can add to the previous answer, was that the reason we also couldn't do this much work in LLMs earlier was that over the summer and the few months leading up to the summer was the time when RAG really became a very popular technique, and there was a lot of research that came up in that area specifically for information retrieval systems. I think specifically about the knowledge distillation aspect, the reason why we chose not to go ahead with that and we picked RLHF was that when we were reading about it, we saw one paper that spoke very highly of knowledge distillation. But when we were looking at how people were implementing it or applications of it, we did not find much use of it in LLMs. It was definitely used more in smaller models, but for LLMs, we felt that maybe this wasn't something that was tested out, and it would have. That we felt like there were higher chances of it being a miss compared to RLHF, which was a more proven technique for LLMs. So for the coming teams, definitely, if knowledge distillation for LLMs has been explored more in the months leading up to their project, we would recommend them to try it out because for smaller models, we've seen it work in different domains. And if it works for LLMs, this would actually greatly reduce the complexity of the models that we use here.
And especially for our use case, we didn't have the rewritten queries in our data set. So that was a major challenge why we didn't go for knowledge distillation, because we had needed to have the input and the expected output. For us, there was no expected output, so our evaluation was a one-hop evaluation. Where we were passing it to the retriever and using the output of the retriever as the evaluation. So we didn't have any trained data set to have our teacher model train and then pass that knowledge to students. So that was a major challenge. That's why we went from knowledge distillation to RLHF.
So you all kind of proposed this plug and play back pipeline, right? So I'm just curious, how does your system change if if the system was supposed to handle like more domain specific kind of queries? Would your system work if you just plug in a new vector database and then is it able to handle that kind of queries and just add on to those queries and still deliver the same kind of results?
Yeah, because that's why we use RAG for rewriting. So we have a retrieval augmented generation. So we have a retrieval before passing it to the LLMs. That retrieval will help us to be able to fit our systems for any domain specific task. So it will help us to get the specific context for the specific team or like specific project that this system has to be used for.
And which vector database?
So from system functionality wise, no, we didn't do any vector, like we didn't do integration, like software based any integration this way. Architectural way, we can say that, yeah, we have a RAG pipeline in place, which ideally, yes, in order to be able to use it in system, it should be extendable using these vector database and have a cloud system around it.
So some improvements that could be done or like some changes that would be needed was that the initial retriever, we were using an index over there, which is built on MS Marco. But for a custom database, we would require the index be built on that. And also for domain specific, we had seen specifically in our few short prompting experiments that when we included few short examples, our generation, like the rewriting generation, would be very specific to the domain. For instance, one of the prompts that we tried out, we had added some examples which were medical related, and then the rewriting, no matter what question we gave it, it would always like generate something based on the medical domain.
And to add to that, in our experiment with, when we are using the black box model, we have realized that the rewriting query is highly dependent on the passage you append to the original query. That's why we mentioned that one of our intention users are for the organization-wise internal search, as we're seeing like all those passages we retrieved from our RAG pipeline would be more relevant to the query and to the to the user intended result. So that's kind of our plan, and we have seen this is feasible and possible in our experiment. And yeah, and as Ishani said, we haven't done any systematic thing to do that, but our experiment does prove that this is possible.
So I have one last comment, which is since you're in the business now of trying to estimate query quality, there's a very important baseline from the IR literature called the clarity measure, which was developed by Bruce Croft and one of his graduate students. And essentially it goes like this. You just do retrieval, and then you cluster the documents that you get back And if you find distinct clusters where the centroid distance is sort of larger, that probably means that the query was ambiguous, because you have groups of documents that are probably about different things. So there are definitely ways you can get at not only looking at things that have a 0 p at 10, but you should be thinking about other queries that really need context and rewriting, and it's ambiguous queries. And there may just not have been enough of those in the data set that you looked at. But in the real world, we all know about how Google comes back and says, did you mean like this or did you mean like that? So you don't want to ignore that, because that's another big place where context can really help. And if you can, what I was thinking about this with respect to your conjecture that querying exogenous sources like Wikipedia could also help with tail queries. What I'm thinking about is, as soon as you're going to start doing this and maybe asking the user for feedback on what to do next, you should definitely think about the clarity measure as well, because it's a proven unsupervised technique that you can use to estimate query quality. All right, thanks guys. Great job.